Hi there, and welcome to Telefunken. Today's video describes the service and calibration of a Precise Model 111 vacuum tube tester. The Precise Model 111 was designed and sold by Precise Development Corporation of Oceanside, New York. It was released in 1954 in kit form at a cost of $69.95. It could also be purchased factory wired for $139.95. The equivalent of more than $1,400 today. Based on a Hickok circuit with a few extra bells and whistles, the 111 was advertised as being the most advanced, most complete, and the best commercial tube tester at any price. In addition to measuring mutual conductance or transconductance, it allows for the measurement of emissions, filament current, grid bias, gas, and even provides an estimate of remaining tube life. With the proper adapter, it can be used to measure the performance of color CRTs. Why am I interested in this device? Well, every electronic lab should have the ability to test vacuum tubes, especially those that profess an interest in repair and restoration of vintage audio equipment. Most recently, I undertook the repair and restoration of a vintage Dynacord tube-based echo machine and needed to test the vintage Telefunken vacuum tubes that came with it. I decided to acquire this tube tester and add it to my arsenal of test equipment to address that and future tube testing requirements. It might not quite live up to the hype of 1954 advertising, but it is a fairly capable tester that should meet those needs for years to come. There are a few good videos on YouTube describing the theory and operation of tube testers, including some on my favorite channels such as Blue Glow Electronics, X-Ray Tony B, The Radio Mechanic, and All American 5 Radio. Jim Leonidas of Jim's Radio Shop has a series of 12 or more videos on the Precise 111, more than 12 hours worth. Rather than try and compete with Jim's content, what I hope to cover in today's video is the service and calibration of this tester in one bite-sized video. While I'm mentioning Jim's channel, a special shout out to my viewers from Orillia, Ontario, because, believe it or not, I do have a few. So what will you need to service a Precise Model 111 tube tester? The first thing I'd suggest is collecting all of the documentation you can find on the machine. The manual, assembly instructions and assembly diagrams, calibration instructions, and schematic are all widely available on the internet. By examining the schematic, you'll see that there are very few components in the tube tester that might be candidates for a replacement. There are a couple of electrolytic capacitors that might need to be swapped out with new ones, and a ceramic disc capacitor that, in my view, deserves to be replaced with a proper safety-rated capacitor. You may have a single paper and wax capacitor in your tester that I would suggest you swap out with a modern foil capacitor. Other than that, there are an assortment of carbon composite resistors that may have drifted over time, and in my case, I did find I had to replace a handful of resistors that were well outside their stated tolerance. You'll need a couple of tubes to assist in the calibration, ideally both a fresh 6L6 and a 6C4 tube. A quick word of caution. As with most tube equipment, the voltages that are used inside this device are potentially lethal. If you follow along with this video, you do so at your own risk. If you don't know what you're doing, please leave it to a professional. Let's get started.
Well, what we have here is a Precise Model 111 tube tester, and this is manufactured by Precise Development Corporation, which is not to be confused with Precision Equipment Corporation. This is a company based in Oceanside, Long Island, New York, whereas Precision is based, I believe, in Illinois. And so this is a tube tester that was made around sometime in the 50s or maybe even early 60s. We're not sure. This was available as a kit. I believe it was also available as a fully assembled unit. I'm not sure which this is. I just purchased this at an auction. However, cosmetically, it appears to be in very good shape. It's known to be quite a useful tube tester in that it measures both transconductance and emissivity, and has the ability to measure plate current, grid current, and has a whole raft of capabilities that are not necessarily in your super budget tube tester. I got this at an auction for a very good price, and one of the measures of the condition of this might be the condition of the tube chart, the roll chart. Oftentimes these things become jammed, ripped, torn, and the like, and don't work anywhere near as the roll chart in this tube tester. In addition to having a roll chart with tube testing data printed on it, this also comes with a manual which has updates to the tube testing chart. And so, for example, supplementary tube data, which tube tester vendors would release from time to time. It also has the build guide, the construction book. And this is available online, as is the schematic and all of the calibration instructions. Before I turn this on, I'm going to turn my attention to any components in this that may have worn out and have the potential to damage the tube tester. Now, what's inside this thing? For the most part, what we see here are a large array of switches, tube sockets, and a couple of transformers. However, these transformers are rather specialized. They have many, many taps for different voltages, either filament or plate voltage transformers. There's one that's dedicated to the filaments and one that's dedicated to the plate. There are 2 rectifier tubes in the tube tester and a number of filter capacitors, a rather small number of filter capacitors, but it's those filter capacitors that I might suspect of failure. And if they were to fail, there's some potential that they could end up ruining these transformers. And if either of these transformers were to be ruined, I think we would find ourselves out of luck, as these transformers are going to be very difficult to come by. So I'll be opening this up and having a look at the capacitors, and depending on how readily available they are, whether or not I have suitable replacement capacitors in stock or can get them in short order, I'll either be replacing them outright or subjecting them to some testing before I use this bit of equipment. I will note that this has a 3-pronged plug on it, and I don't know if it was supplied with this plug or not, but I have seen Jim Leonidas, I believe his name is, has done a number of videos on this tube tester, and in his case the tube tester was supplied with a 2-prong plug that was non-polarized, and he found that there was some voltage potential present on the chassis of the unit. One would assume that this 3-prong plug has been wired correctly and is addressing that potential on the chassis, and we'll examine that and again make sure that this thing is safely wired before we power it up. And when we power it up, we'll be powering it up using our variac and electronic circuit breaker so that we don't subject it to undue strain. So without further ado, let's get the screws off of this thing and see what we can see. So we've removed the 14 screws from the perimeter of the chassis, and I'm just going to put a regular screwdriver under the lid of the instrument, or the face of the instrument, and attempt to lift it up Now this thing is pretty darn heavy, so this may be easier if I put it on its side, although again, it is so darn heavy, it's making me take another look at it and make sure that I've removed all the screws. So we'll tip it on its side like so and tilt it forward. We do have a screw on the bottom, and I'm not sure what that is for. It's possible that that is holding the transformer in place, and I'll take this out. Okay, yes, so that was it. There's a screw in the bottom of the cabinet which screws onto this bracket, and there's only one, although there's room for another here. There's no other hole in the chassis in this case. So I'm going to place this gently on its face and move this cabinet. So as I mentioned, what do we have here? We have a huge array of switches, rotary switches, and some tube sockets, two rather substantial power transformers. I believe this is the power transformer for the filament voltages, which will typically be about 6.3, then 12.6, and so on. And this will be for the various plate voltages and the like. What can we see? We can see, in addition, a number of power resistors, which will undoubtedly be voltage dropping and or current limiting resistors here, and a number of capacitors, such as I alluded to earlier. We see a ceramic disc, another ceramic disc, another ceramic disc, and we see an electrolytic down here. We'll have to have a look at this guy and consider replacing him. The power cord, as I mentioned, is coming in here, and I'll be checking out the wiring of this power cord to make sure that it is properly wired. But what I can see, based on the color scheme of the power cord, we have a black, a green, and a white wire. And what do we see? We see the green wire coming here, and it is indeed grounded with a ground lug to the chassis, which is probably good news. We see the black wire coming in here, and this would be our live wire, and it is immediately going to a rheostat. And this rheostat is going to be adjusting the line voltage, whereas the neutral line is coming in over here, and there's a bulb here which is indicating, which is essentially a fuse. My preference actually would be that the line come through to the fuse first, rather the hot line come through to the fuse rather than the neutral. So we'll consider whether or not we're going to adjust this to try and make it a little bit safer. There are a number of calibration potentiometers on this section. This is the so-called power supply section of this instrument, and that's really mostly what it is the power supply and some elaborate switching and then some metering capability. The meter itself is below here. There's another capacitor across that meter, and we'll check that one out as well. Without further ado, we'll set out to look at this. Again, these are our rectifiers. This is a 5U4, and this is a 6X4. That's right, 6X4 rectifier. And we can see that the builder of this has labeled the various potentiometers right on the chassis of the instrument. This is unlikely to have been done at the factory if this was assembled in a factory, and this suggests to me that this may have indeed been assembled by the end user, although I'll reserve judgment on that until I've had a closer look. Good news is that a lot of these rotary switches are in pretty good shape. Oftentimes, the inner band of these types of switches tends to blacken over time, get very corroded. And the fact that that has not occurred here is probably a good thing. Nonetheless, I'm sure that they would all benefit from a shot of contact cleaner, and they'll probably be getting that as well before I reassemble this. Again, this tube chart is in excellent condition. They tend to get frayed, especially towards the ends, and this one is essentially mint, which is very unusual. Well, I've taken a quick look around at the inside of this precise tube tester, and it's a good thing that I did, because in spite of the fact that this seems to have been reasonably well built, I've identified a fault, and it's one that it is the result of a cold solder joint. This resistor here, which goes from this switch over to this switch, I presume is to be soldered onto this lug, was floating in outer space, and so that's not making a connection. I'll have to fix that. In addition to this electrolytic capacitor here, which is a 3.3 microfarad, where the schematic says that it should be a 2 microfarad, we have a 100 microfarad capacitor, and it's an electrolytic, and it's bridging the meter. I don't know when these were installed, if they're original or not. Something tells me that they may not be, given that they appear to be of a more recent vintage. However, this one seems to be bulging a little bit. The other one, I don't know what kind of shape it's in, so I'll be replacing them. In addition, I have checked a number of resistors, and some of them are well out of tolerance. So we might expect that these carbon resistors would be increasing in value, and indeed some of them are. The tolerance on most of them is 5 or 10%, and some of them are well above 10% in terms of the increase. In fact, some of them are as much as 200%. And so those that I can identify, I will replace. There is a diode over here. It's an early diode. It's a, a 1N51. And I checked it, and it appears to be okay. It seems, I believe that's a silicon diode based on the voltage drop across it, which was about 0.5 volt. So I'll leave that in there. But first things first, I'll take care of those capacitors and any
really wildly out of tolerance resistors. Fix this and be right back. So while examining the schematic for any other potential safety issues, it occurred to me that this small capacitor here linked to PT4 is going directly to ground off of the center tap of the secondary from the transformer. And indeed, if we power up the instrument and measure the voltage across this capacitor, we can see that it's on the order of 220 volts DC. It'll probably descend slightly as the rectifiers heat up. So a failure of this capacitor in the form of a short could be a safety hazard. And so what I'd like to do is replace it with a proper X and Y rated safety capacitor. So I'll be doing that momentarily. So after a fairly comprehensive review of the wiring of this instrument, piece of equipment, tube tester, I have identified a number of out of specification components, mostly just resistors that have drifted. And I've replaced a few of these, and we'll replace a few more. But really the biggest area where I see discrepancies from the assembly instructions relate to some of the wiring around H1, which is the socket for the 5U4 rectifier. Some of that can be accounted for in some of the calibration instructions, which do suggest some rewiring of H1 in response to adjustments that may be required as a result of the phasing of this power transformer, PT4. However, in addition, I found a lug on P9, this lug here, which is lug number 3 on P9, which is supposed to have been grounded in the same manner that many of these other lugs have been grounded to the chassis of the potentiometer. It has not been grounded. And this is a fairly significant error, and that it's going to really screw up some of the voltages that are present at other important parts of the circuit. So this needs to be grounded, and I'll set about to do that. Now I won't be using my normal soldering iron for that. I'll be using this Weller, which is a much heavier soldering iron. I call this Son of Snoz, in reference to D-Lab Snozeramus. And if you're doing soldering directly to chassis and the like, having a heavy soldering iron like this one, this is an SP80, it really makes a difference. This is an 80-watt soldering iron, and it can go to about 1,000 degrees Fahrenheit in temperature. And so we'll set about to do this right away. Just try to gently bend this lug, and it's really pretty tough. It would be a lot easier to do this with the potentiometer out of its socket, but sadly we don't have that option. Get it as close as we can and then apply a big glob of solder to that. And that seems to have done it. There we go. And I'll just very quickly verify that this is truly grounded, and it is. In some cases, these potentiometers may not actually achieve a ground, or rather connect to the chassis directly. But in this case, this one does. So in addition, I'll be changing this resistor here, which is meant to be a 4.7K resistor. It's drifted to 5.9, which is more than 20%. And it is a 10% tolerance resistor. So I'll change this out real quick. Yes, 5.9K. And it's not supposed to be 5.9K. It's supposed to be 4.7K. And so we'll just
swap this guy out. Okay. Is both of these operations complete? Well, what we have here is the precise Model 111 tube tester on the bench, tipped on its side, and I've changed the electrolytic capacitors, reconnected a detached resistor, and gone through and changed one or two out of specification resistors, and checked the pilot lights and indicator lights to make sure that there is conductivity so that we're not misled by any failure of these lights to illuminate properly. And we're about to go through the calibration instructions and make sure that the unit is working properly. So hopefully you get a good view here with the cameras that I've got set up on the bench, and I'll try to whip through the 2 pages of calibration instructions as quickly as I have. The first thing in the calibration instructions is an admonition to make sure that after building this unit, one checks their wiring. And my assumption is that this unit has been built properly and was working at some point. However, I have checked the wiring, and as I indicated, I found a detached resistor. So I consider this step to have been done. And then we're to initiate the operational procedure. We are to set all internal controls on the power supply chassis to their maximum clockwise position. So these would be these trimmer potentiometers and the like. I'm not going to do that. This is because, in part, my assumption is that that has been done. So I'm assuming that any remaining calibration as a result of resistors drifting and the like is going to be relatively minor. And so I'll assume that this has been done, yet I'll follow all the other instructions to the letter. And if I deviate from them, I'll let you know. And I have done the wiring check indicated in the calibration instructions and have adjusted all of the controls to their full counterclockwise position. The test switch is on hold. The line pot is on the middle position. The meter slide switch is to normal. The bias slide switch is to 10 volts. The off life on switch is to off. That's this switch right here. And we're going to check the resistance from terminal number 16 of the power transformer PT4 to ground. And we're looking for at least 50,000 ohms. And we can clip on to the small ceramic capacitor lead here, which goes to 16. And if we turn our voltometer to resistance, we see that we have a resistance of 224K. And so that is greater than 50,000 ohms. We can move on to the next check. And that is to check the resistance from ground to pin 7 of the 7-pin miniature socket on the power supply chassis. Now that's not the 7-pin socket here on the front face of the tester, but rather it's the socket again on the power supply chassis. This is the power supply chassis, and it's the last pin, and I will clip onto that. And there's a resistor attached to it, which provides us with good purchase, and it is 11.4K. It's supposed to be around 8,000K. Again, we have not adjusted the trimmer potentiometers to their full travel, so this value may be off slightly, but it's greater than 8K, and that's fine. So now we're to connect an AC voltmeter from ground to terminal 14 of power transformer 4, and we'll do that. Lead 14 is the one that is
closest to the center, and I'm going to have to tip the tester forward here. So it's the one closest to the center on the bottom of power transistor, power transformer 14. Apologize. And we're on volts, and we are to then plug the line cord into any 110 volt, 50 or 60 cycle outlet and push power slide switch to on. And the pilot light should light immediately. And if it doesn't, turn it off at once and check the pilot light and the filament transformer winding. I'm plugged into my Variac and electronic circuit breaker, and I'm giving it 125 volts. I'll turn that down slightly to 120 volts, which is nominally my local voltage. And again, just checking this, push the power slide switch to on. And when I do that, we do see the pilot light, and I can set the line adjust control for a 5 volt AC reading. And I need to make sure I'm on 5 volts. We've got about 5.2 volts, and I'm turning counterclockwise, and that is coming down. And I'll just move this test lead out of the way here. If I turn counterclockwise, I can reduce this value, try to get it as close as I can to 5 volts. This is a wire wound rheostat, so its precision is going to be somewhat limited. I think that's about as close as we're going to get. 5.02 volts, 5.03. So step 12 is, without changing any of the above settings, adjust the internal line potentiometer for a center scale reading on the tube tester meter. And I can do this, though there are a couple issues. So P9 is this potentiometer right here. However, one of the things we might want to be wary of is that we have the instrument tipped on its side. And so we'll disconnect from these voltage measurement points. And very carefully reposition the meter. We find that we're very close to that 0 point. However, we can get closer by adjusting P9. We'll do that. And we've done that. I'll tip this back up so we can see what we're doing. Again, this was P9 that I adjusted to get the center position on the meter, which again is not quite at center because we have the instrument tipped on its side. So we're about 1 mark to the left of center on the top scale, which is the GM scale. So we're at step 13. Without changing any settings, connect between ground and terminal 2, the center arm of P5, and adjust for 2.8 volts. Again, ground, clip on here, and P5 is apparently way down here. I'm just verifying that. There's P5 and there's P5A, and so we want to be on the center lead of P5, terminal 2. I'll just position the volt ohmmeter test lead on that position, which is not super easy, but doable. Thank goodness for these little alligator clips, or these grabbers. And we are to adjust for 2.8 volts AC with an AC vacuum tube voltmeter with a high impedance. Now this has an adequate impedance to facilitate this type of adjustment. It doesn't say explicitly what to adjust, but my assumption is that we're adjusting P5. There we are. It's a little stiff, that's all. 2.817, 2.818.
And as we turn counterclockwise, we're actually, oh, there we go. We're actually increasing the voltage, and it's clockwise we need to go in order to decrease the voltage. Gosh, and this is very, very sensitive. 2.84, 2.83, 2.81, and 2.96. Okay, that's as close as we're gonna get. I can just extract my screwdriver. There we go. 2.796.
That's as close as we'll get to 2.8. And so we can move on to the plate bridge balance section of the instructions.
The next step in the calibration is the plate bridge balance. And first thing we are to do is temporarily attach a resistor, a 2K 10 watt resistor from ground to switch 2, the test switch, position 11. And there is a typographical error in this version of the calibration instructions. The version of the calibration instructions in the original manual is correct. It says switch to position 11, and this version of the instruction says switch to position 1. So that just a cautionary note there. You do not want to attach this resistor to position 1. You want to attach it from ground to position 11. Otherwise, this step in the calibration will not work as it should. So we turn all of the controls, A through O, to their full counterclockwise position. Filament bias counterclockwise, short to test normal, meter to line, and test to off. And then we can apply power to the instrument. And when we let it warm up, what we are to do is adjust the line so that we are in the center position. We'll just let it warm up for another few seconds here. And again, we're adjusting the line voltage so that we have the center position. And after that has been done, we're supposed to be switching the meter to test. And we see we're now at 0. And when we turn the test switch to test position, we're expecting to see a deflection from this 0 position. And we do. We see a negative deflection. And in order to adjust for this, what we do is we adjust potentiometer P4, which can be accessed from beneath the instrument. And you need either a very steady hand or a non-metallic screwdriver in order to make this adjustment. Or both, frankly. And again, we are adjusting this with a view towards minimizing, if not completely eliminating, the deflection from 0. Now we have positive deflection, negative. So after some careful cleaning of the potentiometer P4 with deoxit fader F5, I have managed to get the potentiometer adjusted to a point whereby when I switch the test switch from off to test, although there is initially a minor deflection on the meter, which could be positive or negative, depending on where in the cycle I move the test switch, it settles back at the 0 deflection point. And that's exactly where we want it. And so I consider this to have been adjusted. And now we can move on to the GM adjustment portion of the calibration. And before we do that, we switch off the instrument and remove the resistor, which is attached to switch 2 between ground and position 11 on switch 2, as opposed to position 1 as erroneously described in the rewritten calibration instructions. So again, something to watch out for. So now we come to the GM adjustment, and we're to set the controls on the front panel for a 6C4 tube as shown in diagram A in the manual. And this is diagram A here. And so I'll just run through these settings.
The filament voltage is to be set at 6.3 volts. We are to have the plate shunt at position E, 3000, GM at GM, screen voltage G, plate voltage G, EM shunt 0. F should be set at 4, G 0, H 6, I 5, J 0, K 1, L 2, M 0, N 0, O 0. The test switch should be set at test, or rather off. I apologize. The meter switch should be set at test, and the short switch should be set at test. And what we do next is we turn the power on. We also have the bias setting to 10, turning on the power, and we put a tube into 6C4, and the first thing we do here is we evaluate whether or not this tube has any shorts, and we expect the short light to come on in positions 1, 3, 4, and 5 of the short switch. So this is the short light here, comes on in 1, no illumination in 2, 3, 4, and 5, and should be out in the remainder of the positions. And it is. So we put it back to test. We now rotate the test switch to hold, and we rotate the meter switch to line and adjust the line control for a center scale reading. Now, we're going to be making some adjustments that are going to be influenced considerably by the position of the meter, and accordingly, I'm going to tilt the tester on its side. Here we go, or rather on its back. And this way we get appropriate parallax on the meter. So with the switch to line, we adjust the line so that we have center deflection on the meter, which we do have now. Then we rotate the meter switch to bias, and we rotate the bias control such that we have 10 volts on the bias voltage reading. And this is the bias voltage on this portion of the meter. And we're looking for 10 volts of bias voltage. And that's 10 volts right there. Now we're to repeat C and D, because there's the possibility that by adjusting the bias voltage, we've affected the line voltage setting slightly. And again, we go to bias voltage adjust and make sure we're at 10 right on the button. There we are. We rotate the meter test switch to test and note the reading on the 3000 GM scale. And so that scale is right here, and we have a reading of approximately 2,380. And then we're to rotate this switch to the 6K setting, which means that the meter is now reading GM on a different scale. And what we're hoping is that we're going to have the same reading. And if I examine the meter, this is a little bit more challenging to get a precise reading, but I'm getting about 24, I'm just getting a little over 2,400 on the 6,000K scale. And so we should be adjusting P5A on the power supply chassis to get the same reading as we had on the 3,000 scale. And so we'll adjust P5A, and you can't see this, but P5A is another one of the plastic potentiometers, and I'm going to be adjusting this to slightly reduce this reading, and that means adjusting it clockwise. So we have approximately 2,300 and maybe 80. So I believe that's about where we need to be, right there. Now we repeat this step, but we move this to the 8K range, and we adjust potentiometer P6. The 8K scale is shown here. It's the lower of the two scales on the top, and we have approximately, again, we're a little hot here. We have slightly above 2500, and we should have roughly 2380, and we're adjusting, in this case, P6. Okay, that's about right. So again, I'll go back to the 3K and double check this. Just, again, some very minor adjustments. And I think we're about where we need to be. So we'll turn this off and go on to the GM screen balance and voltage adjustment. First thing we'll do is we'll remove this tube, which is one of our reference tubes. We'll move this, rotate switch C to position A, and rotate switch O to position 3. 1, 2, 3. Now we're connecting a DC voltmeter from the plate jack to chassis ground. Use one of these old school. That should do it. And chassis ground. We have a voltmeter here. And set it to AC. DC, rather. We rotate the bias potentiometer to 0 and the bias switch to 50. Turn the instrument on. Rotate the meter switch to line and adjust the line adjust for center scale. Adjust P14 for 60 volts on the DC voltmeter. We're pretty darn close, 60.4. P14.
P14. Now P14 is one of these recessed potentiometers, so we have to be a little careful that we're not shorting anything out here as we do this.
60.01, 59.8. This is drifting slightly, so I think we're going to be leaving that right where it is. Okay, now we're going to adjust the front panel controls for a 6L6 tube as shown in diagram B of the service manual. And that again involves a 6.3 as a filament setting. The plate shunt should be on setting B, 20K, and GM-EM should be set to GM. This should be set to G, 0, 2, 6, 4, 3, 1, 0, 5, 2, 0, and 0. This is to be at off, this is to be at test, and this is to be at test. We set the line adjustment to center deflection point and then return this to test. And we can insert a 6L6 tube. So the 6L6 goes in this socket right here. Turn the instrument to the on position and we wait for the tube to heat up. And we'll do the short test where we should see a short on position 2 and 7. Now, we know that we should see in addition a short on 1 in this particular instrument, and we see one on 2, goes out on 3, 4, 5, 6, 7, we see it again, 8, 9, and 10. So coming back, we see it again on 1, bring it back to test. Return the test switch to off and turn the instrument off. I'm skipping J, which is a test that is to be done after moving leads back and forth. And I'm moving forward to step M, rotating the plate shunt switch C to 8K, and repeating steps B, rotating the meter switch to line, adjusting the line control for 0 bias, or rather midpoint, switching the meter switch to line and adjusting the line voltage to the middle deflection point, rotating the meter switch to bias and setting the bias slide switch to 10, and adjusting the potentiometer here so that we have 10 volts of bias, and then repeating this to ensure that we have not dropped our line voltage. Bias at 10 volts, that's done, and rotating to test, and noting the GM reading on the 8K scale. So according to this, the GM on the 8K scale, which is this scale here, has just dropped slightly and is approximately 1950, although it's climbing slightly. It's 2000, still climbing slowly. So it's approximately 2000 on the 8K scale, which I'm writing down. And so this is not a particularly great tube. And now I'm to turn this to the 20K scale. And I should see around 2000, and I don't. I see above 2600. And so I'm to adjust potentiometer P7. P7. Okay, that's adjusted. And now this is to be turned to 30K and repeated. And 30K is to be read from this this scale here, and it's currently reading again about 2500, and adjust potentiometer P8 after resetting the line and the bias, which is still roughly the same. Now test and P8. Okay, now I'm going to go all the way back here and repeat. So again, checking the line is in the middle deflection point. Bias is at 10 volts exactly. And test gives me a GM of 2000. Okay, so I'll come back to 20K, repeat this, line still in the middle, bias still at 10, and test. And it gives me exactly 2K on the 20,000. And 30, go back, check the line, it's still the same, bias, still the same, and test, it's giving me, well, it's reading a little, oh no, it's giving me just a little bit more than I should be getting. So I'll just adjust this slightly with P8. P8. Done.
Well, we have tried somewhat unsuccessfully to calibrate the emission readings on this precise model 111 tube tester. And this was done using this tube, which is a 6L6, which actually came with the meter when I purchased it. And it has written right on it, lousy tube, emissions are low, bad, etc., etc. And indeed, the GM readings are also a little low, much lower than they should be for a tube like this one. And so we're trying this again. Rather than using this 6L6, which is an electro-harmonics tube. These tubes are made in Russia. We're going to try it again using a JJ tube, and these are made in the Slovak Republic. And this is a brand new tube, and accordingly we should expect it to have fairly healthy emissions. I have set up the instrument according to the instructions using the settings illustrated in diagram C of the manual. And what we are to do is connect a negative side of a milliammeter to the plate jack and a positive side of a milliammeter to the grid. And you can see here I have my Fluke 867 connected.
and we see a 60 hertz signal with 20 milliamps of current. And I can adjust that using the bias knob here. And previously I was unable to get to 20 milliamps of current. And so this is a victory in of itself. And then after we set it at 20 milliamps, which I'm attempting to do, there we go. We're to adjust potentiometer 11 on the power supply chassis, and I'll do that using this screwdriver. And we're to adjust this so that it reads 3 on the 0 to 10 volt bias scale on the meter. And we're at about 2.5, and I'm turning it clockwise and it comes up past 3. Turning it back just a little bit, it's kind of touchy. And that's about it right there. So that's that done. That's the emission calibration established. And we can go on to the filament current calibration, which I will do now. And that means we turn the test switch to off. We remove the leads going to the grid and the plate. And we can turn our meter off. We rotate the meter switch to 3 amps and rotate the meter switch to line and rotate this to line, adjust for center scale, which we have. We now turn this to 3 amps and adjust P12 for a reading of 0.9 on the 3 filament amp scale, and that is the second bottom scale. And we're currently at approximately 0.85. So P12 is in the bottom right-hand corner, and again, using a screwdriver, just adjusting this ever so slightly, getting us to 0.9 amps. And that's that.
Now we are to remove this tube. I'll just turn this off for a moment. Gently extract the tube, and we'll insert the 6C4. Here we go. Then what we do is we rotate switch H to 5, H to 5, and switch I to 6, to 6. Make certain the test switch is in the off position. Filament switch should be at 6.3, and insert the 6C4, and we have. Meter switch should be at line, and we should be able to adjust line voltage, and we'll do that. And line voltage is coming down as tubes heat up a little bit. Then we rotate the meter switch to 0.3 amps and adjust potentiometer P13 for a reading of 0.15 on the 0.3 amp scale. And so 0.15 would be center, and P13
is above P12 on the far right top of the power supply chassis board.
And that's that adjusted. And we've now completed the calibration.
That's all for today's video. I hope you found it useful and entertaining. Thanks for watching and have a great day.